All right, today we're going to talk about something that's all around us, from the smallest ripple in a pond all the way up to the light traveling from the most distant galaxies. We're talking about waves and optics, the fundamental language of nature itself. So let's jump right in.
Okay, I want you to picture this. It's early morning, everything is quiet, still. You're looking at a pond, and the surface is like glass. Now, you toss a small stone right into the middle. Suddenly, that stillness is broken. You see these perfect circles, these ripples spreading out. It's beautiful, right? But what are we really seeing when we look at that?
Well, that ripple, that's a wave. And all a wave really is a disturbance that's moving energy from one place to another. Now here's the really important part. The water itself isn't actually moving across the pond. Nope, the little water molecules are pretty much just bobbing up and down in the same spot. It's the energy from the stone that's traveling. The energy moves, but the stuff it's moving through, the water, stays put.
So, we know this energy is on the move. But how does it actually do that? Well, it turns out there are basically two main ways that waves get around.
Okay, so you've got two types. First, there are transverse waves. This is like our ripple in the pond, or even light itself. The particles move up and down while the wave itself moves forward. So the motion is perpendicular. The best way to picture this is just shaking a rope up and down. Then you have longitudinal waves. This is how sound travels. Here, the particles push and pull back and forth, parallel to the direction the wave is going. Think about a slinky. When you push one end, you see a compression travel all the way to the other side. That's a longitudinal wave.
Now, to actually talk about and measure waves, scientists have a specific set of terms. Think of it like a toolkit. You've got wavelength, which is just the distance from the top of one wave to the top of the next. Then there's frequency, which is how many of those waves pass by you every second. Amplitude is pretty simple. It's just how high the wave is. And of course, you've got the time period, how long it takes for one full wave to go by, and the wave velocity, which is exactly what it sounds like, how fast the whole thing is moving.
And what's so cool is that these things aren't just separate ideas. They're all connected by this one beautiful, super powerful equation. V equals F times lambda. The velocity of the wave is just its frequency multiplied by its wavelength. I mean, think about that. If you know how close together the waves are and how fast they're coming, you know exactly how fast the energy is traveling. And this isn't just for water. It works for sound, for light, for everything. It's universal.
Okay, things get really interesting when you have more than one wave in the same place at the same time. I mean, what happens? Do they collide and bounce off each other like billiard balls? Do they just pass right through? What goes on?
So, yeah, what does happen when two waves try to occupy the exact same spot?
The answer is actually way simpler than you might think. They just add together. That's it. It's called the principle of superposition. You literally just take the height of the first wave, add it to the height of the second wave, and that's your new wave. It's a really simple rule, but it leads to some pretty wild results. This simple addition gives us two main possibilities. First, you have constructive interference. This is when the peak of one wave lines up perfectly with the peak of another. They add up, and boom, you get one giant wave. But what if a peak meets a trough? Well, if they're the same size, they completely cancel each other out. For just a moment, there's nothing there. And that's called destructive interference.
Now, this whole idea of waves adding up or canceling out, it might sound like just a neat physics trick, but it's not. This was the key that unlocked one of the greatest mysteries in the history of science.
Let's go back to 1801. A guy named Thomas Young sets up this famous experiment. He takes a screen, pokes two tiny little slits in it, and shines light through them onto another screen. Now, if light was just a stream of tiny particles, like little baseballs, you'd expect to see just two bright lines on the back screen, right? One for each slit, but that is not what he saw. Instead, he saw this bizarre pattern of many bright and dark stripes, and he realized this is an interference pattern. The bright spots were where the light waves from the two slits were adding up, constructive interference, and the dark spots, that's where they were canceling each other out. This was the moment, the smoking gun. It was absolute proof that light behaves like a wave.
So, okay, light is a wave. That discovery really blew the doors open for understanding how light works, which is basically the entire field we call optics. Let's start with something we see every day, reflection. You know, looking in a mirror, it's all about light bouncing off a surface, and it follows this really elegant, simple rule. The angle the light hits the mirror is the exact same angle that it bounces off. That's it. Perfect, simple symmetry every single time. But what about when light doesn't bounce off something, but actually goes through it, like from air into water? Well, this leads to that classic trick of the eye that we've all seen.
You know why that pencil looks bent, right? It's because of something called refraction. See, when light travels from the air into the water, it actually slows down, and that change in speed forces it to bend, to change direction. It's this bending that's the secret behind pretty much everything in optics. Lenses in your glasses, the camera on your phone, giant telescopes, they all work by bending light. And of course, we can calculate all of this with some pretty neat formulas. You've got one for lenses and one for mirrors. And just look at how similar they are. The only difference between them is a single plus or minus sign. That's it. That tiny little sign change is the entire mathematical difference between how a lens bends light and how a mirror reflects it. Kinda cool, right?
Okay, so let's zoom out for a minute. Let's take all these ideas and see how they fit into the biggest picture of all, the universe.
Remember, we started this whole journey with just a tiny ripple in a pond.
Then we saw how the very same rules apply to the sound waves that carry our voices and all the music we love.
And then we took it to the most cosmic scale imaginable, realizing that light waves travel across billions of light years, carrying the story of faraway galaxies right to our eyes.
When you look at it that way, from the tiniest ripple to the entire cosmos, you realize this isn't just a topic in a physics book. Waves and optics, this is the language of nature itself.
And that kind of leaves you wondering, doesn't it? If this is just one of nature's languages that we've managed to figure out, how many others are out there, all around us, just waiting for us to learn how to listen?